All right, part D, final question. This one's worth 2 points. In total, how many cubic feet of snow are on the driveway at 9 a.m.? Okay, one more time. How many cubic feet of snow are on the driveway at 9 a.m.? This one should be screaming at you fundamental theorem of calculus. Because we know when we started, we had no snow on the driveway. Okay. Plus, how much snow falls starting at 0, or I guess starting at midnight and going until 9 a.m. Well, that function is 7te to the cosine of t dt. Again, keep in mind this is a calculator active question. I have absolutely no intention of doing any integration trickery. I'm not going to try substitution. I'm going to type this into my calculator. This is how much snow falls. But we also need to take into account the fact that Janet has been removing snow from the driveway. So we're going to subtract off from this how much snow she's removed by 9 a.m. We could, if we chose to, use our answer from part C. Right? Part C, we built h of t, which was the function that says how much snow she has removed at any particular time. We could use the last piece, which I think we just said was 108 times t. In this case, the t for us is 9. And then we subtract off from that, I believe we said it was going to be 631. And this is how much snow falls. This is how much snow is removed. Snow removed by Janet. If I subtract those two results from one another, the answer that I should get on my calculator is going to be 26.334 or 26.335 cubic feet. And that's it. That was the final part. I think the trickiest part for me anyway, as the teacher and approaching the question, was part C. It was just a strange question. But A, B, and D, I think are pretty typical questions. You should expect to see a question like that next Wednesday on the exam. Good luck. Okay, our last sample AP question comes from the 2007 Form B exam. It was question 3, which means it's calculator active. We are going to take great advantage of our graphing calculator, its ability to solve equations, its ability to find values of derivatives. This one is definitely going to test our conceptual understanding of calculus. So let me read this question to you. The wind chill is the temperature measured in degrees Fahrenheit that a human feels based on the air temperature, as well as the wind velocity. Wind velocity is measured in miles per hour, and the temperature is measured in degrees Fahrenheit. We're told that if the air temperature is 32 degrees Fahrenheit, then the wind chill factor can be determined by this function, W of V. So the wind chill is a function of the velocity of the wind outside. W of V is going to be 55.6 minus 22.1 times V to the 0.16 power. And it is valid for V between 5 and 60, which means that we're going to be able to use this if the velocity of the wind outside is between 5 and 60 miles per hour. Now, where does this equation come from? Don't worry about that. I'm sure our meteorologist friends can go through the derivation. All we need to worry about as calculus students is we have this relationship, we have this function, and we have our variables, we have our units, and now we're going to be asked a bunch of follow-up questions. A, we're going to be asked to find W prime of 20. We're going to find the derivative of W. Using correct units, we're going to explain the meaning of W prime of 20 in terms of the wind chill factor. Part B, we're going to be asked to find the average rate of change of W over the time interval 5 to 60. Furthermore, we're going to be asked to find the value of V at which the instantaneous rate of change of W over the interval is equal to, Part C, over the time interval 0 less than or equal to T less than or equal to 4 hours, the air temperature is constant it's 32 degrees Fahrenheit. At time t equals 0, the wind velocity is 20 miles per hour. If the wind velocity increases at a constant rate of 5 miles per hour, what is the rate of change of the wind chill factor with respect to time at t equals 3 hours? Indicate the units of measure. All right, let's do this. Let's just jump right on in. Here comes part A. Okay. Part A. I want to find W prime of 20. Well, W prime means we're going to take the derivative of W. We could, depending on your comfort level, you could type this function in as y1 into your graphing calculator. You could then use your calculator to take the derivative of this function at 20, and that'll give you a numerical answer. That's great. You'll probably get 1 point for that, but then you're going to have to explain your answer. That's one way. The other way is you could use your general power rule. W prime of V, let's take a derivative. 55.6 is a constant. Derivative of a constant is 0. Minus 22.1 times V to the 0.16 power. Although those might be some ugly decimals, we're going to use our general power rule for derivatives. And the general power rule for the derivatives, I have a constant times a variable being raised to a power. I'm going to bring the power down, times my variable to the 1 less power. That's W prime of V, that's our general derivative. W prime of 20, I'm just going to, everywhere I had V, replace that with 20. We'll have negative 22.1 times 0.16 times 20 to the 0.16 minus 1 power. Going to be really careful with my placement of parentheses. My final answer is going to be negative 0.2855. The exact same answer that I would have gotten out of my calculator if I simply graphed it and used the dy dx button. But here's where we need to be careful. We need to explain that answer in terms of the context of the situation. And here's where we want to be really careful. We took the derivative of W with respect to V. We treated V as our variable. So this answer over here represents dW over dV at the time when V is equal to 20. Now the units for W was our wind chill factor, and that is measured in degrees Fahrenheit. V is the velocity of the wind outside. Velocity of the wind outside is being measured in miles per hour. So in terms of explaining my numerical answer is going to tell me that when the velocity of the wind is 20 miles per hour, then my wind chill factor decreases at a rate of 0.2855 degrees Fahrenheit for every mile per hour. One more time. When the velocity of my wind is 20 miles per hour, then my wind chill factor decreases at a rate of 0.2855 degrees Fahrenheit for every mile per hour. I know that's a mouthful, lots of opportunity to get tripped up on the units, but just pay attention to the units, let the units be your guide. Don't worry about the fact that you may not be comfortable with this concept of degrees Fahrenheit per miles per hour. Just let the units be your guide here. Part B, we want to find the average rate of change of W over the time interval 5 to 60. All right, well, let's start there. The average rate of change of W over the time interval 5 to 60. So in order to do an average rate of change is just like slope. How do we find slope? We look at the change in y over the change in x. Well, our variable here is they're not y and x. We're looking at a change in my wind chill factor over the change in my velocity. So I need to find out what the wind chill factor is when the wind is 60 miles per hour. I'm going to subtract from that the wind chill factor when the velocity of the wind is 5 miles per hour. I'm going to divide that by 60 minus 5. When I did that, again, I used my graphing calculator, and what I got this time was negative 0.2538. The units are degrees Fahrenheit per mile per hour. Again, your wind chill factor is measured in degrees Fahrenheit. Velocity of the wind is being measured in miles per hour. Change in W over change in V. It carries all the way through. That was the first part of this question. Now we want to find the value of V at which the instantaneous rate of change is equal to this average rate of change. Now, average rate of change means slope. Instantaneous rate of change means that we're going to take a derivative. So we need W prime of V. Now this is something where your calculator will be helpful, but not quite as helpful as it was before. What I need is I need for W prime of V to be equal to my answer of negative 0.2538. Well, W prime, we already figured this out before, is negative 22.1 times 0.16 V to the 0.16 minus 1 power. That's the expression on the left. That's our instantaneous rate of change. We need to know when is that equal to negative 0.2538. At this level, the calculus is done. We took the derivative on the left. We want to know when is equal to this value on the right. You could enter this into your calculator as y1, enter that into your calculator as y2, find the intersection. You could, if you don't like that, you could move this negative 0.2538 over to the left. You could graph what's now on the left-hand side as one equation and figure out where it's equal to 0, so you could find the root. No matter what method you use, as long as your answer is accurate to 3 decimal places, you should come up with V is equal to 23.010. V is your velocity. It's the velocity of the wind. So your final answer will be 23.010 miles per hour. That's it for part B. On to part C. All right, part C. Over the time interval 0 less than or equal to t less than or equal to 4 hours, the air temperature is a constant 32 degrees Fahrenheit. That's important. At time t equals 0, the wind velocity is 20 miles per hour. So when t is equal to 0, the velocity of the wind is 20 miles per hour. The wind velocity increases at a constant rate of 5 miles per hour per hour. Another way to say that, for every hour, the velocity of the wind increases by 5 miles per hour. So in terms of calculus, I'm going to write this as dv dt. It's increasing, that's by 5 miles per hour every hour. Okay. What is the rate of change of the wind chill with respect to time at t equals 3 hours? So what I want now is dw dt. How does the wind chill factor change over time? Specifically, I want it at t is equal to 3. Well, let's go through and let's do this. If I want to take the derivative of my wind chill function, the wind chill function was given to us as W of V equals 55.6 minus 22.1 V to the 0.16 power. Well, if I want to take the derivative of W with respect to time, maybe what you're thinking now is, hey, this is like those related rates problems from earlier in the course. Great. Maybe you see this as a chain rule. I bet if you are at Southwest and you're looking at this problem, you're probably not seeing it as a chain rule problem, because I know we haven't done a lot of problems this way. Let's see if we can approach it as a related rate. Maybe that's going to be the way for us to attack this. The wind chill factor is a function of the velocity of the wind, but I want to measure the wind chill factor, how that changes with respect to time. So I'm going to go over to the right side of the equation. I'm going to take its derivative. Derivative of 55.06, that's a constant, that's 0. minus 22.1 times the derivative of v to the 0.16 power. That'll be 0.16 times v to the 0.16 minus 1 power. Hold on, you're not done. Don't put your pencil down. We're measuring how things change over time. What we just did is we took the derivative of v. But v, the velocity of the wind, is changing over time. So we need to multiply this by dv dt. That, if you're able to follow that stream of logic, you're able to come up with that derivative equation. Outstanding, we're almost there. Now what we need to do is we need to evaluate this whole function at t equals 3. So I'm going to have to figure out, well, the 22.1, the 0.16, the exponent, all of those are constants. That's not the problem. I need to figure out v when t is equal to 3. I need to figure out dv dt when t is equal to 3. Some of these have been given to us. Some of these are going to take a little bit more work. Let's keep going. dw dt evaluated at t is equal to 3. Maybe a little bit of calculator work could simplify this a little bit. Negative 22.1 times 0.16, I believe, is going to be negative 3.536. V, 0.16 minus 1, negative 0.84. I still need to figure out v when t is equal to 3. I'm then going to multiply this answer by dv dt when t is equal to 3. Well, how is the velocity of the wind changing at 3 hours? We were told earlier that dv dt is a constant rate of 5 miles per hour, which means that dv dt is going to be 5. What we still haven't figured out, though, but we're making some great progress here, is what is the velocity of the wind when t is equal to 3 hours. In order to do this, let's pull back from the problem just a little bit. We were told, but we haven't used this fact, that at time 0, the velocity of the wind is 20 miles per hour. Additionally, we were told that the velocity of the wind increases by 5 miles per hour per every hour. So that means after 3 hours have passed, the velocity of my wind has increased by 5 miles per hour for every one of those hours. What that means is that my velocity is going to be, I'm going to have negative 3.536. The velocity is going to be 35 miles per hour. That will be raised to the negative 0.84 power. I'm going to multiply that by 5. Thank goodness all of those are constants. I'm going to rely on my calculator, and what I'm going to get out of this is negative 0.892. That's the numerical answer. We are almost done. We need to pay attention to our derivative. We're measuring how the wind chill factor changes over time. Wind chill factor is measured in degrees Fahrenheit. Time is being measured in hours. So this rate means to me that after 3 hours, the wind chill factor is decreasing at a rate of 0.892 degrees Fahrenheit per hour. We are done. Amen. Hallelujah. We've got it. We've earned all of the points. Congratulations. And with that, we get to wrap up this video. There are exactly 7 days left between now and the AP exam on Wednesday, May 4th. Good luck to all of our friends at Southeast, at North Central, at Southwest, and across the district if it's not the year 2011 and you're watching this video right now. Good luck.